Hi folks, welcome to chapter 20. If you haven't already watched the Against All Odds video regarding t-distributions, please do so and then watch this video. As we've seen before, we always have to have conditions for inference, any kind of inference about a mean. So here are the conditions that are needed for a realistic inference about a population mean. If you recall, with chapter 16 and 17, we knew the population standard deviation sigma, but that's not very realistic. Now we actually get to do some problems just using the sample standard deviation, which is going to be great. So it's more realistic to gather data from a sample, a smaller subset of the population, and then glean some information about the population, aka inference. So conditions for inference about a mean: we have to have a simple random sample. Remember from chapter 18, that's really important. This is always important, a simple random sample, as we have seen. Observations from the population have a normal distribution. That's sort of important. A sample size being large enough is even more important. Basically, it has to be, you want it to be symmetric and single peaked, unless the sample is very small. Both mu, population mean, and sigma, standard deviation of the population, are unknown parameters. So conditions for inference about a mean: our sample, if it's going to be large enough if the population is at least 20 times as large. Previously we assumed that we knew the population standard deviation, like I said, sigma, but now we don't. So our next thing is going to be that we know the sample standard deviation. So that's that S divided by the square root of n, as we see here. This quantity is called the standard error of the sample mean. So S divided by the square root of n is the standard error. Standard error, when the standard deviation of a statistic is estimated from the data, the result is called the standard error of the statistic, as we have seen. The t-distributions: when the sampling distribution of x is close to normal, we can find probabilities involving x by standardizing, just like we did before. So, as you guys recall, what did we do when we standardized? We did z equals x minus mu sigma divided by the square root of n. That's standardizing. We don't do that anymore. This was our old school curve. Remember, we took any kind of thing where we knew the mu, so like IQ was 100, and then we standardized it and we went to the mu being 0 and used table A, if you recall. So we used table A. So now we don't know standard deviation of the population. We're going to use S. So what do? This is a new kind of distribution here. This is our t-distribution. The new statistic does not have a normal distribution, but it's really, really close. It kind of looks like this. The only difference is that this distribution, there's more area out here in the tails, as you also saw in the Against All Odds video with Party. So our t-distributions, when we standardize based on the sample standard deviation S, our statistic has a new distribution called a t-distribution. It has a different shape than the normal curve. It is symmetric with a single peak at 0, just like our standard normal curve. It has more area in the tails. The t-statistic has the same interpretation as any standardized statistic. So it says how far x bar is from the mean. That's what we did. Those are the standard deviation units that we talked about before. There's a different t-distribution for each sample size, specified by its degrees of freedom. That's what I always like to think of when I hear degrees of freedom. And it's just a fancy n. You take your sample size minus 1. That's all it is. Okay? So you just take 1 away from the sample size. All right. The t-distributions. When we perform inference about a population mean mu, a t-distribution, the appropriate degrees of freedom are found by subtracting 1 from the sample size n. So there we go. We call these the degrees of freedom. It is symmetric with a single peak of 0, has more area in the tails. The one sample t-statistic and the t-distributions, the only difference, you guys, is what? With the old one, this was a z and this was sigma. Okay, so we're going to use the same stuff, same formulas. When comparing the density curves, we can see here they show the standard normal curve. If you can see that, that's in purple. Then we have degrees of freedom with 9 degrees, so that would mean that your sample size in here would equal 10. Your sample size here of 2 degrees of freedom, then your sample size is 3, and that's the standard normal curve. The cool thing about this is as we increase our sample size, as n gets larger, then our t distribution gets closer to the standard normal curve. So it gets more accurate because remember, we are not able to use the population standard deviation anymore. We can only use the sample standard deviation. So if you have a small sample, you're going to have a standard deviation that might be a little off from the population. So that's why the curve up here is higher off the ground, and it kind of gives us a little more wiggle room. We have to, when we're calculating our confidence intervals, for instance, with the t distribution, we're going to have a wider confidence interval because we don't know the sigma, the sample or the population standard. Just like before, you guys, we had chapter 16 confidence intervals, right? Using Z statistics. Chapter 17 significance testing using Z. Now the only difference in chapter 20, what are we going to do? Chapter 20 is all about T's, okay? So we're going to use the T's. So this is how you find it in table C. You've got this degrees of freedom is on the left-hand side of your column, so you're going to go down. And if you have a sample size n equals 12, then your degrees of freedom is going to be 12 minus 1. That's 11. So your degrees of freedom right here. So you go down to that 11 column where the degrees of freedom are, and then what do you want? You want a 95% confidence interval. So we're going to do a 95% confidence interval. In table B, we consult the row. Just like we said, we move across that row to the entry that is directly above the 95% confidence interval. So this appears, I believe, on the top of our table C, and you'll see that on the top. And the probability, the tail, is actually on the bottom, and we'll get to that shortly. So the desired value is 2.201, and just like before, remember what our confidence interval was? X bar plus or minus, instead of a Z, which we used to have, that critical Z, now we're going to have T star, and instead of sigma on the top, take a moment to think, what goes there? Instead of sigma, S. Remember what that difference is? It's the sample standard deviation divided by the square root of, not 10, the square root of n. Okay. A one sample t confidence interval is just like what I wrote. There you go. You've got it right here. Okay, moving on. Here's our example. So, does the expectation of good weather lead to more generous behavior? This is like the example in your book. Psychologists studied the size of the tip in a restaurant when a message indicating that the next day's weather would be good was written on the bill. Here are tips from patrons, 20 of them, measured in percent of the total bill. That means that n equals 20. So, just right off the bat, what's the degrees of freedom? You guessed it, it's 19. Here's our sample. So what do we do with these? Well, I want you to pause the video and I want you to enter them into your calculator and see if you get the same X bar and sample standard deviation, remember, in your one variable statistics button, okay? So take a moment to do that right now before we move on. So we want to estimate the mean tip for comparison with tips under the other conditions. So we're going to estimate the mean percentage tip mu for all patrons. Remember, that's what confidence intervals do. They capture that mean. And when they receive the message on their bill indicating that the next day's weather will be good by a 95% confidence interval, checking conditions. Do we have a simple random sample? The study was actually a randomized comparative experiment. As a consequence, we're willing to regard these patrons as a simple random sample from all patrons of the restaurant. So here we go. Normal distribution. What can you do to ensure that you have a normal distribution with your sample? Stem leaf plot. You could do a histogram on your calculator. Ask your calculator to do a histogram and check it out. Make sure it's roughly symmetric. Stem plot doesn't suggest any strong departures from normality. Sample size is 15, so we're comfortable with using the t-interval. We can proceed with the calculation. Did you all get this 22.21 for your x-bar and your sample standard deviation of 1.963? Hopefully you did. Degrees of freedom are 19. We already calculated that. And that means then if we were to look in table C, T star 2.093. Did you all get that? Remember, you go down the column to the 19 of degrees of freedom, and then you look at your 0.95, and right here where they meet up, you're going to get the 2.093, and then all you have to do is put in the numbers. So you got your x bar 22.21 plus or minus, because it's a confidence interval, and then you've got your t star 2.093, which you found in table C. And then you've got standard deviation 1.963 divided by not the degrees of freedom. We're still just doing square root of 20. Okay? And I think I'm going to write over myself, but the idea of this is that we got that 21.29 to 23.13% tip. Is that a pretty good tip? Is that higher than normal, would you say? 20% is pretty average for tipping. Okay, we are 95% confident that the mean percentage tip for all patrons of this restaurant when their bill contains a good message that the weather is going to be nice is between 21.29 and 23.13. The one sample T test, just like we did a one sample Z test. Do you remember that in chapter 17? So now we're doing the one sample T test. Only difference is a T and a different table that we're going to be using. I promise to show you guys how to use this all in our calculator very soon, but for this lesson I kind of want you to just use table C. So draw a simple random sample of size n from a large population having an unknown mean. To test the hypothesis, compute the one sample T statistic. In terms of a variable T having this distribution, the p-value for a test, it's just like it was before. Like I said, T's not Z's this time. And on the last one, just to point out, you do 2 times the p-value that you get. P-values are exact if the population distribution is normal and are approximately correct for large N and other cases. So we're going to do an example. Ohio considers it unsafe if a 100 milliliter sample of water contains more than 400 coliform bacteria. Here are the fecal coliform levels found by laboratories at 20 Ohio State Park swimming areas. This stuff is real. We've tested these. My husband works for NRCS, and they've done local testing of the fecal coliform in our rivers and streams. So once again, I want you to pause a moment and calculate the mean and see if you can find the standard deviation of the sample with this. Is this good evidence that on average the fecal coliform levels in these swimming areas are unsafe? So this is a significance test that we're going to do, but instead of Z's, we're using T's. So the null hypothesis is the level is not unsafe, and the alternative is the level is unsafe. That's kind of confusing the way that they're saying that, but think about what your null is and what your alternative is. And we're going to go and check it out. 400, that is the population so far. So that is not unsafe. That's good. If it's greater than 400, then the level is unsafe. All right, so we're willing to regard these particular 20 samples as a simple random sample from a large population of possible samples. Hey, that's not symmetric about the mean, is it? Large population of possible samples, the histogram of 20 samples doesn't let us judge normality, but the data are somewhat skewed. The sample size is larger than 15, so it's safe to use the one sample T test, but tread lightly, okay, if you were to do this in the real life, right? p-values may be slightly off. See that? That's definitely for certain. Based on x bar, this is what we got. Did you get that on your calculator? And did you get this for your standard deviation? The one sample t statistic is this. So once again, the only difference here, you guys, this is S. We were using sigma before. See, there's not much of a difference here. You calculate that one sample t statistic. This is where it gets a little tricky now, okay? So the p-value for t equals 3.583 is the area to the right of 3.583 under the t distribution curve with degrees of freedom n minus 1. This shows, the diagram is shown in the book, so you could look at this example because it's in the book. Here's my t distribution. Remember, we're assuming that our sample mean is 400, or our population mean, and then this would be my area shaded over here. This would be because it's greater than, and we want to assume that. So here we've got our 1, 2, 3, 1.3, and I need to find this p-value here. So we'll show you how to find the exact p-value. It's really nice in your calculator soon. But for now, I want you guys to, whoops, I want to go back to that, calculate it in your books. All right, so that you guys could see the entire table and I could show you on one page. I kind of just pieced it and cropped this, cut out a bunch. So go to table C with me and check it out, and you'll see that with table C, I did my picture here, and we've got our degrees of freedom. Remember, our degrees of freedom are 19. So what we're going to do is we found our critical value to be 3.580, and we're going to go along the degrees of freedom row of 19. So I'm going to try to underline it best that I can. And then you're going to look for that 3.583 in between. It's not 83, it's 3.580. See how it ends up right here? It's somewhere between 3.579, 3.883. So then what I do is I go down to the bottom of table C. See, this is a one-sided P because remember our alternative hypothesis was that the mean is greater than 400. That was the safe level. And so it's a one-sided. Remember, a two-sided would be if your alternative hypothesis was that the mean was just not equal to 400. In this case, we want to just make sure it's not greater than 400 because that's the safe limit. So it's not this one. So we're going to go to the one-sided, and what you do is you're trying to find what these say. This gives a p-value. We can't do the p-value like we did in table A before. The t distributions are just too much. It would be a huge table if you can imagine, because you have all your different degrees of freedom that you're looking at. And so what we're going to do is we're going to take this number, the two numbers that sandwich that 3.580, that's right in the middle, and we're going to circle them, and we know that our p-value is somewhere between 0.0005 and 0.001. Notice that I had to switch them around because as you go farther and farther away from the center of your distribution, your p-value gets smaller and smaller. See that? I also just made this connection because in the previous drawing I put 400 and 1, 2, 3, 4, 1. Remember when we standardize t equals 0, the middle, and then we've got 3.580. This is actually the mean goes to, we're standardizing it to the mean of this t distribution is 0 and that. So we know, can you tell that this is pretty sufficient evidence to assume that these are unsafe limits? So we're going to write our conclusion right now. So we can conclude, because the p-value, if you see, it's in between, that p is less than 0.001. So there is quite strong evidence with the p-value less than 0.001 that fecal coliform levels in these Ohio State Park swimming areas are unsafe. Excuse the handwriting. But basically the main idea that I want to show you guys, it's between here, but the one that we care about is the bigger p-value. Remember our significance levels back in chapter 17.05 is usually our cutoff unless specified otherwise. You can see that this is much smaller. This p-value is much smaller than 0.05. So we can reject the null hypothesis and assume the alternative that fecal coliform levels are greater. Okay, 2 more parts, you guys. Hang in there. Matched pairs T procedures. Comparative studies are more convincing than single samples investigations. For that reason, one sample inference is less common than comparative inference. Study designs that involve making 2 observations on the same individual or 1 observation on each of the 2 similar individuals result in paired data. When paired data result from measuring the same quantitative variable twice, as in job satisfaction study, we can make comparisons by analyzing the differences in each pairs. If the conditions for inference are met, we can use the one sample T procedures to perform inference about the mean difference. So let's go back to the job satisfaction idea. If you do a survey about the how content you are with your job, and you take the survey before, and then maybe your job wants to implement more break times, more times for walking, more times for social hangout, and then they do that same test afterwards, they would take the matched pairs would match your test beforehand, and then after they implemented their improvement on quality of life in the workplace, and they would take the difference, and that's what we would measure. We're going to do more examples in class in Zoom on Tuesday to look at this. So to compare the responses of 2 treatments in a matched pairs design, find the difference between the responses within each pair, then apply the one sample T procedure of these differences. So it's just applying the same T procedures. We can do this with confidence intervals and with significance tests. Robustness of T procedures. This kind of brings us back to chapter 18 again. So, a confidence interval or significance test is called robust if the confidence level or p-value does not change very much when the conditions for use of the T procedure are violated. So, except in cases of small samples, the conditions that the data are a simple random sample, population of interest, is more important than the condition that the population distribution be normal. Sample size is less than 15. You can use the T procedures if the data appear close to normal, so you want them to be roughly symmetric and single-peaked with no outliers. If the data are clearly skewed or if outliers are present, do not use T. Sample size at least 15, the T procedures can be used except in presence of outliers or strong skewness. Remember, we saw that example where we had our histogram that was definitely skewed to the right. We still proceeded, but we looked at our p-value and we just were cautious about it. Basically, with all of our examples, you can run the T procedures, but just keep that in mind about the strength of your test when you're performing these and writing your conclusion. Large samples doesn't really matter. As long as you have a large sample, you can use the T procedures even for clearly skewed distributions. And that goes back to the central limit theorem with our sampling distributions, because we know our sampling distributions are pretty normal. Thanks for being such a patient audience and such a good audience. I'll see you guys in Zoom this week, Tuesdays, Thursdays, 3 to 4, and you can also join our support class from 1:30 to 2:30 in Zoom. Have a good night.